Just maybe a hello everyone. Just a quick announcement. We posted an assignment yesterday. It's a simple. Oh, the one he's saying he's in St. Peter's and the rain is hard there. It was around PM, 5 p.m. It was also heavy,
Okay.
raining hard. Okay, good. Well, not good. I don't know. I hope you didn't get caught by the rain. But anyways, so there is an assignment there. Did anybody see it? Read it? The mini project proposal, exactly. Manuel. Can you tell what it is about briefly, please, Manuel?
I just opened it because I didn't receive the notification, and I
Oh,
just
it was weird.
yeah. Well, it says that we need to identify a paper with an application of a network science and try to reproduce it.
Yeah, Professor, maybe some suggestions regarding the paper,
Okay.
the papers that they can choose from.
Yes. In the web page, there is a in the web page there is a place where there are about 15 papers. I don't know if. Let me share my screen.
Yes, that would be nice. So I think this is a very important step to get
Yes.
familiar with the data science methods. So, sorry, network science methods. So it's just a matter of reading, choosing a paper, reading it, and then try to do some of the work, replicate the work that they did. In some cases, as you will see, maybe it's a lot of work. So maybe just even a portion of the work would do if it is too much for just the short time that we have. But it's very important because that's a very a good way to get familiar with the network science methods. Professor, go ahead, please.
Okay. Are you seeing my screen?
Yes, we are.
Okay. Here is the web page of the course. In the last uh, tab, there's projects. Okay. If you click here, there are this first link is networks with research article. So if I open here and there it's a zip file, you can extract the zip, and there's okay, not 15, only six, please. Uh, Here is a football network. Okay, let me, if I can see the network. I don't know if, okay, I guess in Gephi. And there's about articles about the network. Okay, if you like football or interested in sports, it's a very it's a very important topic of network science. Uh, I don't know. Wait a minute.
Anybody interested in football? Well, football this would be like the British term, because the Americans call it soccer, which is kind of weird. So it will be football, right, actually, the real football, not American football.
Okay. Uh, okay. the network is not visible, but uh, and there are other networks, political blog, uh, 5 or 6 networks with articles. But in internet, there are a lot of networks. There are sites with hundreds of networks and research articles. So you can choose. Uh, so you can see the networks here. This is this other link. It's a Stanford University uh, class projects of 2009. A lot of projects the students of a postgraduate course in network science made. And here is the students, the title of the article, and the PDF of the articles. There are a lot. For example, examining online poker as a social network, mechanism of network shrinkage due to stress. There are so these two links are in the web page, but you can find a lot of uh, more more networks and research articles in the internet. And the idea is to choose an article, to read it, to understand it, and to try to replicate with the tools, with the technological tools we are going to explain here in the course, the article. That's the idea of the mini project. It's all right, Luis Fernando. It's correct.
Yes, 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 Professor. And for now, you just have for the next week. You all you have to do is to pick the paper, to read it, and to understand what you will have to do. And then, like in a few weeks, you will have to deliver the results of your analysis. Okay, so that's going to happen quickly. It's like you already have the data set, you already have the tools, the software tools, and we'll continue studying some of the concepts today, so you get more familiar with whatever you need to do.
Okay.
Okay,
Yes.
I think we can then continue, Professor. Oh, you wanted to show some of the reports,
Okay.
right?
Look. I guess this is network data repository. I guess I don't know if this site. This is an interactive scientific network data repository. A lot of networks, thousands, I guess. And if you choose one network, I guess here are the properties of the network. Oh, this no. These are different networks. If you click here,
Yeah, it's a data set, each one of them, right?
this is the
Uh,
properties of
t-
the
uh,
network.
Teacher,
Okay.
you can repeat the process. I lose
Yes.
in before the repository.
Okay. I do
Maybe
it very, very
can you
fast.
share the link, the website here on the chat, please?
Yes.
The link?
I'm gonna share it in the chat.
Yes.
It's a very good repository of networks.
Thank you.
So here you can explore, look, social networks, biological networks, brain networks, collaboration, economic, infrastructure, technological, road networks, retweet. Okay, this is a very good repository. So you have plenty of sites, plenty of networks that you can choose for your mini project. Okay.
Thank you.
Okay. Okay, I'm gonna begin with this big thing, centrality measures of a network or of a graph. This is a very big topic. There are a lot of measures, local measures of a graph. The principal measures are four. We are going to talk about these four centrality measures that are the most important, but there are a lot. Okay? Uh, Objectives, it's about identifying the important or influential nodes in a, here's a mistake, not in the system, but in the network, okay? Centrality measures are critical in a wide range of applications that involve concepts, phenomena such as vulnerability, robustness in transportation system, the internet, urban system, efficient communication within a network. What nodes are important when you need efficient communication in a network? Dissemination of information, the spread of diseases. In social networks, power, the notion of power is very important, of control. The spread of information in the social networks, these are applications of centrality measures of a network. And this is the first one, one of the most important centrality measures, and one of the more simple. It's degree centrality. We are going to measure the importance of a node in a network by its degree. So this, for example, this node has degree 5, this node has degree 4, and this is the first measure, important measure of a node in a network, okay? Okay, depends on the degree of the node. The number of neighbors is better, maybe it's better to talk about neighbors of a node. Number of neighbors is the degree. We have talked a little bit about nodes with high degree centrality are often referred to as hubs in technological terms, or as influencer in a social network. In a network like TikTok, like Twitter, uh, person that had a lot of friends, or people who connect to that persons, they become influencers. The degree centrality is important in terms of social networks, but also in terms of other types of networks. For example, electric networks, because an electric network could be vulnerable to attacks. So if you have a node in the electrical network with high degree and it's destroyed, the network could be broken, could suffer a lot, okay? All these have to be with degree centrality. They are efficient channels for spreading information. For example, the node here, if this node here want to spread information to this guy here, the information passes through this guy. So high degree sometimes implies that efficient channels for spreading information. Changes in degree centrality over time, or differences in degree centrality between networks can provide insights into evolving relationships, behavior, or structural changes. This is important. We are not going to deal with temporal networks or dynamic networks that vary over time, but seeing the evolution of a network in terms of how for example, a person in a social network is gaining friends, is gaining people who follow them. It's important because those persons in which the degree or the number of neighbors is increasing could be very important in the future for the social network. Okay, so also in dynamic networks that vary over time, this degree centrality is important.
Professor, I think, yeah, the concept is very intuitive when it comes to social networks. And I think Juan Sebastian is giving a nice example. He says that the green and red nodes are similar to what we call in communications and in computer networks gateways. Why is that, Juan? Can you develop and explain maybe
Okay.
for those non-computer scientists? One?
Yeah, like I was thinking that it was very similar to those, but not to be confused, of course, networks in terms of network science and the communications, but of course they are related a little bit. So it's like the blue one is like a local network, and the gray ones are like another local network separated, but the communication between them can be through a gateway. That'll be red and green nodes. So it's interesting because here's the same idea, because you have to get to them to communicate between each other. And that's more or less how internet works, but on another scale, of course.
Yeah, and it's very important to, like in the case of the social network, like, intuitively, like an influencer is because, whatever this person says, it's known by many people at the same time, right away. You don't need to go through several steps, right, Professor? But in just one single step, everybody knows the information that they post. In similar is in the communication networks is something similar, like because the data go through that computer, let's say, or that node rather, and then you can spread the information to all the like in this case as you illustrated, a very good example actually to the blue nodes. So immediately, not you don't need to go through several steps to get there to each one of those nodes. So I think it's a very nice example, right, Professor?
Yes, yes. We are going to see in 5 or 10 minutes that these red and green nodes have another property that is not degree centrality but other centrality. The degree centrality is important in the diffusion of information, but in the control of information, there's another type of centrality. It's called betweenness centrality. And in the case that the information spread very fast, we have to consider another centrality that is called closeness centrality. We are going to talk about these other two centralities that are very similar, but it's important to know the difference. So these red and green nodes, a part of being of high degree centrality, they have also another properties. Okay. Okay, this is a simple example of the measure of the nodes in the network. Here at the left, we have the degree centrality that is very obvious. And here at the right, you have the normalized degree centrality. I don't know if it's clear, this normalized degree centrality. Why is important the normalized degree centrality?
Wait, Professor, maybe one of the students can like make sense of the numbers or give an explanation why
Okay.
what it means, just by looking at the numbers. What is that normalized degree centrality? How do you compute it? Can anybody explain it? How do you compute it?
How is computed this fraction? It is clear, or someone could explain?
Yes, I think they can do it.
Maybe the edges over the nodes that is related.
No.
One. One is given one.
For
One.
example, why is red node one half? Why is one half in normalized degree centrality? Any ideas?
I guess that could be the initial number divided by the number of nodes. So for example, 6 divided by 12, that is the number of nodes, is equal to 1/2, I guess.
Exactly. Exactly. When you divide the the degree of a node by the total number of nodes, you get the normalized degree centrality. Why why this normalized degree centrality could be important?
Wait, Professor. One. So, what is
Yes.
the intuition then, Manuel? There. So, what idea does it explain? Or provide when you take that measure?
Okay, I think that is a way to put a degree of centrality between 0 and 1, taking into account the links of the node and the total number of nodes.
Okay.
Yeah, but does it give any idea? Like if you measure that centrality, the normalized degree centrality, everyone, does it give you any idea how connected the node is to the rest of the nodes of the network? Does it give any idea?
Yes, of course. That is precisely what it does.
Ivan, can you explain, please?
Well, I mean, uh, i- if you get this number, you can just tell from it precisely, as you say, how connected a node is to all other nodes within the graph. So that is a quick first approximation to the centrality of a node. I think you said it pretty clearly.
Okay, thank you.
Okay, but a question: What is best? What is best to know that this node had 6 of degree centrality, or that this node had one half?
Well, if you knew it had
What is most
six,
important of the two?
if you knew it had six connections, but you did not know how many connections were there in
Exactly.
total, that wouldn't tell you much.
Exactly. This normalized degree centrality is very important for comparison of different networks. If you have another network that where a node has one half of normal centrality, you are thinking in that node is that person is friend of half of the network, okay? Half of the network is, and the network could be small, could be big. So this is very important for comparison of different networks in terms of the degree. It's clear?
Is it clear?
Okay.
Cool. Yes, please. Please, whenever we ask or say anything, just reactions are welcome. Okay. Thank you.
Okay, we're going to see a simple model in NetLogo of this concept. Let me. One second. For example, here, this node has degree 6. I could go to another node, and this model shows the degree of each node. So it is very clear what is the degree. Here are all the degrees of the nodes. Here are the normalized degrees. An important visualization tool is the following. Look at this. What are you seeing here? Why the colors? This is a very useful and a very common visualization of the degree centrality of a network.
Can anybody make sense of the colors there? What do they mean? Can anybody?
Yes, of
May-
course.
Maybe the
There are
weight.
It's the density.
Okay. Who said the density? And can you explain, please? I know that several of you spoke.
It seems to me like density because it's between more neighbors, the color gets more opaque.
More darker. Okay.
Dark. Mhm, exactly.
It goes from black to white. Black are the nodes with
I
most degree and white less degree. In a network that is big, for example, 50 nodes or 100 nodes, this visualization is very important because you at a glance could see a global distribution of the degrees. Okay. Another visualization, I don't know if, let me show you, is this, okay? By size. So here you're visualizing the degree of a network, not by color. Uh, I'm gonna erase the color. Okay, I'm gonna let the color, but this is by size, okay? Okay, like that. The same color, but this is by size, okay? The tools that we're going to work, Gephi and NetworkX and all the technological tools that are used for researching or for discovering properties of networks, use that layout of the networks. Okay. I don't know if this. Okay. Look here. It's not very clear, but we have talked about this important concept. One of the most important properties of a network is the degree distribution. Okay. It's like a histogram where in the x-axis is the nodes, and in the y-axis are how many nodes have, excuse me, x-axis the degree, and y-axis how many nodes have that degree. Okay. Closeness centrality. Second important measure of a node in a network. Closeness centrality measures how close a node is to all other nodes in the network. Nodes with high closeness centrality can efficiently communicate with other nodes and have quick access to information or resources. They are important for understanding communication efficiency. If you are going to spread an information from a node with high closeness centrality, the information is going to flow faster. It is often used in transportation networks to identify nodes with quick access to various destinations. Okay, this is a mistake. Okay. It's like a geographic center. It has to do with geography, is because when you talk about closeness or farness, you talk about distances, no? You are never far from the action. You are in the center of the action. For measuring the closeness centrality, we have to use shortest path lengths. We're going to see this in a moment. And how can you define closeness centrality? It's very easy. I think it's best if we talk about farness. Okay? What is the farness of a node in a network? Very simple. You have U is a node. You look for the distance from you to the other nodes in the network. For one node is distance 2, for other node is distance 3, and you sum all these distances, okay? The sum of all these distances from one node to the other nodes is what is called the farness, okay? If you divide this number, the farness, by the number of nodes, you obtain like a normalized farness, okay? And if you do the reciprocal of the farness is the closeness. So if farness is 4, closeness is 1/4, 1/4, okay? Let's see the model to clarify that. Okay. For example, this simple network. Let me see.
By the way, what type of graph is that? How do you call it? Guys, we read you.
Yes.
What
A
type
very
of,
important graph.
okay, Paula, a tree, exactly.
Tree.
Exactly one. Particularly in this case, could be a binary tree, exactly. Thank you.
Okay, I'm gonna do clicking length of shortest path. Look. The closeness centrality of this node is 1/2. Look, the distance from this node to this is 1, to this is 2, to this is 3, to this is 3, to this is 1, to this is 2. If I sum all these numbers, 1 plus 2 plus 3 plus 3 plus 1 plus 2, it's 12. 12 is the farness. And the total number of nodes, not including the one that I am considering, is how many? 1, 2, 3, 4, 5, 6. Okay, so 12 divided by 6 is the normalized farness, and 6 divided by 12 is the closeness. I don't know if it is clear.
I don't think it's so obvious. Maybe you need to go to the math professor because it's like
Okay, let me put another example. Let me put another
I
example.
mean that the difference between what you mentioned about 6/12 or 12. I mean the farness or the closeness. You know,
Okay, let me put this example. What is the closeness centrality of this up here? I'm going to sum the distances from this node to the rest of the nodes. Here, distance 1, to this, distance 2, distance 3. The total distances, the total sum of distances from this red node to the blue nodes is 1 plus 2 plus 3, 6, 8, 10, 11. Okay? 11. How many blue nodes? 6. So 11 divided by 6 is the farness. Okay? And what is the closeness? 6 divided by 11, the reciprocal of the farness. Okay. These are all the values of the closeness centrality. Also, we can do it by color. This is the node with the best closeness centrality. And look, this is the node that is far from the rest of the nodes. And you can see also by color, this is the most central. This is not so central in terms of closeness, okay? Okay, It's important to know, guys, ladies and gentlemen, that we're not going to be worried too much by the calculations, of the centralities. Some calculations, this is a little bit complicated. The next is more complicated. But what our objective is to know that this node is the central node in clonal centrality, because the largest distance from this node to any other node, it's only free. It's free, for example. The largest distance from this node to any other node is 1, 2, 3, 4, 5. So intuitively, this is more central in terms of distances. Okay. Uh, all the software that we're going to use calculates automatically all these. I'm going to I'm showing you how to calculate this centrality. Okay, I don't know if there are questions about it.
There's no question. See, I think this explanation was very clear, Professor.
Okay.
As usual, any questions, just raise your hand or open your mic.
Next, centrality measure, one of the most important measures, betweenness centrality. Let's first say general things about this centrality. Nodes with high betweenness centrality often serve as critical bottlenecks in the network. These nodes lie on many shortest paths between other nodes, meaning they control the flow of information, resources, or influence. This is important. They act as bridges or intermediaries connecting
The
two
cultural
parts.
resource
Look, for example, this is important.
as
This node,
are interviewed critical parts.
look, this node is not good in degree centrality, okay? It has only degree 3. Yes, it is clear? But this is very, very important in between centrality, because all the paths that go from other nodes, from this node to this node here, from this node to this node here, have to pass through this node. So although the degree centrality of the node is low, the between centrality of this node is very high. All the flow of information have to go through this node. Okay? It's different. Between centrality and closeness centrality are different. Closeness centrality have to do with distances, but between centrality have to do with flow of information from nodes to other nodes. I don't know if it's clear the difference. What is going to happen is, when you have a network, it's very probable that the nodes with high between centrality also have high closeness centrality. Yes. In fact, this node is high in between centrality, but is also high in closeness centrality because it's near to the other nodes. But there are networks where a node is the biggest in closest centrality in a network, but not the biggest in between centrality. They are different. I guess this difference is not so easy to at the beginning to understand it. Okay. I don't know if there are questions.
I think the intuition is clear, but let's go to the math.
Okay. We have here a node B, and we're going to calculate the between centrality of this node. What are we going to do? We're going to consider all the shortest paths that go from some node of the network to another that go through B. Okay? For example, all possible paths from this node to this, from this node to this, all possibilities. Okay? A lot of possibilities. This node, I want to connect them to this node. Pass through this node, okay, we have to include it in the sum, okay? So this is a sum, and then we divide by all the shortest, by the shortest path that go from S to T. If we have S here and T here, so what we are measuring is the percentage of shortest paths between all nodes that pass through here. Let me show you an example. Okay, we have this network. The between centrality of node 5 is maximum because all paths that go from the other nodes to other nodes have to pass here, okay? If this is an information network, all information that flows, this person is going to know that information, okay? No way. But if I build a path from here to here, now one could talk with 2 without having to deal with 5. So the between centrality of this node is reduced, okay? Okay, I don't know if it's clear the idea.
Yes, teacher, is clear.
Yes, this is
But look,
example that you made
yes,
have the closeness centrality
yes, I was going to say
different
that.
from the between centrality.
I was going to say that the closeness centrality is maximum also of this node because this node is near to all of them. It's very interesting that you could think for a moment in a network where the node with maximum closeness centrality is going to be different from the node with between centrality. It's not easy. It's not easy. And you think how closeness could be different too. It's a good example to appreciate the difference. It is different to be near to other persons than to be the recipient of the information to other person. It is different. I have an example, but I don't know if it's a very good example. The example is like this. I have ¿cómo se dice tienda o almacén?
Shop, store.
I have a store. Thank you. I have a store in a town, but I have not Rappi. I it's a restaurant, but I don't deliver uh, domicilios. See, I don't deliver domicilios. Where where have I? Where am I going to put that restaurant? in the geographic place with maximum closeness centrality. Okay? Because the people are going to the restaurant, there are not. But if you have Rappi, you have to put it in the place with between the centrality. Okay. Let me go to a model here, another model that I have in NetLogo for.
Professor, while you do that, I don't know if they can think of some other examples where you can use
Okay,
either
yes.
measure, like one of the two measures to make a decision. Like the one, I think the example that you gave is very nice and it's very intuitive. But can anybody think of how to use these centrality measures to make a decision regarding some particular situation, like whatever type of network you have? Can anybody think of an example where these measures of centrality can be useful? Okay, who is this?
Thank you,
What?
teacher. So I think that a good example could be bridges between towns. So, for example, there are some bridges that even though could be it has only two or three edges, they are very important between cities. Even though they has a very short amount of edges, they are very important for the flow of information.
Okay, like bridges.
Okay,
Bridges.
yes.
Yes, that's a good example, right, Professor?
Something like this figure, okay?
I think somebody else has
Something
another
similar
example.
to that figure. Okay.
Somebody else has another example. Doesn't
Yeah, well, perhaps not an example as such, but I would like to say, I would like to notice that we generally think of the center of something as what is most important about it. So these measures allow us, for instance, to know about the optimal way to tackle a problem because they point towards the essence of it, or also towards the heart of a system. So whatever it is that one's modeling with a network, the center is always going to be of the utmost importance to whatever one is trying to do. By definition, I mean to say.
Okay, I want to say what you have just said in a different way. Networks have no centers. The center depends on what you are researching, on what you want to do with the network. Network had a lot of centers, but depending on what you are looking, for example, it is possible that this node could be a center of a network, and this is in the periphery, but maybe there's some reason why this is in the center. For example, there's one important centrality that we are going to deal in 10 or 15 minutes. That said, a node is important if it's near a node that is very important. For example, if you are friend of a person who is very famous, very close friend to a famous person, you could influence that famous person. So you could have more power than the person. For example, in some presidents have consultants, okay? Some mayors of cities have consultants. These consultants are very important for the mayor or for the president because they have influence over him. So they made them the center. And this consultant could be in the periphery. Very few friends, He could live in a town very far from Bogota, but the president or the mayor call call him and said, okay, I have a problem. Could you help me with that? So this node could be central. I don't know if it's clear that. Okay. Any more questions? Okay. Do you hear me?
Yes, Professor.
Yes, we
Yes.
can.
Okay. A little calculating this between centrality. It's by hand. It's very difficult. Here are some basic notes. Okay, I'm gonna ask you a question. Why it's a six and a six here? Why six? Any idea?
Stephanie
Okay.
says nodes, number of nodes.
think-
Says
Oh, it's a coincidence. It's a coincidence. It's not the number of nodes. Okay, it's
I
a
think is the
coincidence,
number of
but
the
it's not the
shortest
number of
paths
nodes.
that I think is the number of the shortest paths that go through that node.
Exactly, exactly. There are six paths from the other node that pass through this node. Look, I have three nodes here and two nodes. I have three nodes on the right, two nodes on the left. So there are how many paths? Three times two, six. And the six paths, shortest path from these nodes to this node, pass through this node. From here to here, one. From here to these two. Here two, here two. Okay? This is the important measure. How many paths pass through the nodes? So these two are going to have high between centrality and this node. Okay? When you divide by 10, 10 is all the possible shortest paths of the network. We obtain the between centrality of the node. Here is 10 because there are 5. Okay. Because there are 6 nodes, and how many possible combinations of pairs of 6 nodes is 6 times 6 of 5 nodes is 5 times 4 n times n minus 1 over 2. So this is 10. Okay, the details of the formula you could find it in the internet. Ask to ChatGPT to explain it. The important thing is betweenness is different from closeness. Closeness different from degree. Okay. Okay. Let's see. Let's see an application of these three centrality measures. A very nice application. We're going to see a video of Andrew Beveridge. It's a neuroscientist of England. He has a video that I want to share with you. It's very short, but I want to put attention because he's going to analyze a very important network, a very famous network with these centrality measures. Okay? So I'm going to share in the chat the link. and Luis Fernando is going to show us the video, okay? It's a very short video, but it's very important that you put attention to what he said.
Okay, I'm gonna share it. Sorry about the ad here, just for a few.
Jueves de 7 a 10 a.m.
Sorry. Here we go. And let me see if you have subtitles. Please, there you go. Okay, so now we're ready.
This is the third and final video on basic centrality measures for networks. In our last video, we talked about degree centrality, closeness centrality, and betweenness centrality. Today, we will put these measures into practice by looking at a classic network example from 2003. As a reminder, here are the intuitive ways to think about these three measures. First, degree centrality measures how many links you have. Second, closeness centrality measures how centrally located you are in the network. And third, betweenness centrality measures how important you are for the flow of information through the network. So let's see what these centrality measures can tell us about the social dynamics of a group of dolphins living.
If you allow me, Professor, just I think this is very important, the intuition, right? Maybe about the three measures before moving on, going on.
Yes. Yes, very important, the intuition.
So how connected are you to the rest of the nodes? How close are you in the center, like of the actual network, like in the middle somehow, intuitively, of course. And here is so this centrality tells you how efficient is the communication. I mean, if you are like good to enable the communication between the rest of the nodes of the network.
Yes,
right?
It's a very good summary of the
three measures. Okay. Nice, very nice. Let's move on now to the dolphins.
Through the network. So let's see what these centrality measures can tell us about the social dynamics of a group of dolphins living in Doubtful Sound, New Zealand. This network appears in a collaboration between David Luceau, a biologist, and Mark Newman, an applied physicist. Their data came from 7 years of research observations, including a tally of which dolphins were spotted together. Luceau and Newman used this data to create a dolphin social network. They joined two dolphins by an edge if they were seen together more frequently than random chance would predict. So here is the resulting network. What do our three centralities tell us? Try to guess the top scores in each of our metrics: degree centrality, closeness centrality, and betweenness centrality. Of course, this network is really too big to analyze by hand or by eye, so just use your intuitive understanding of these measures to estimate who the important players might be. So pause the video and give it a go. So let's look at three different visualizations of this dolphin network, one for each of our centrality measures. First, we size and color the vertices according to degree centrality. And when we do this, we can see that the larger group of dolphins have more high degree individuals. And in particular, the three most popular dolphins are far removed from the second and smaller group of dolphins over here. And then in the smaller group, there are some popular dolphins there too, but there's only one of them, B Scratch, that actually has connections outside of the smaller group. Next, we size and color the vertices according to closeness centrality. And this measure is biased towards the larger community as well. And of course, this makes sense since that's where most of the dolphins are found. But we also see something interesting. This dolphin, SN100, has the highest closeness centrality, even though they do not have high degree. Finally, we're going to size and color the vertices using betweenness centrality. And this visualization tells a profoundly different story. There's only two dolphins that really stand out here, SN100 and B Scratch. So apparently these are the dolphins who are holding this social network together. So we applied our 3 centrality measures to this dolphin network, and we found some popular dolphins and some cohesive dolphins. Lusso and Newman draw particular attention to dolphin SN100 in their paper. Apparently, the network fractured when that dolphin disappeared for an extended period of time. And they cite this convergence of network structure with observed behavior as evidence that the network perspective is a valuable tool in understanding the social dynamics of these mammals.
I had just
Very nice, very nice. Yeah.
Okay, any questions about this video? I agree with Luis Fernando. Very nice. It's a very clear example of
Maybe if they can tell something about, if just by looking at one, what the centrality measures would be enough, or do you actually need some of them, or what information do they actually provide regarding the network and the nodes in the network? Can anybody develop a little bit about that? Like even in the case of the dolphins or whatever situation you can imagine? Can anybody explain? So is it important just to study one of the centrality measures, or do I need maybe to look at some all of them to analyze it?
Well, each measure really says something completely different because uh, 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 centrality as such is something like uh, uh, I mean, that's just what is most connected. But then closeness is somewhere near what is most meaningfully connected. Because I think these short paths are somewhat like meaningful connections, you could say, across a variety of contexts. And then finally, the other measures, just like what is most, it's as a wider approach, not regarding the system's nodes as such, but the system entirely, trying to envision what is most essential to the system as such. So I do think each measure says something completely different.
Yes, and I think it's summarized here, right, Ivan and everyone? In this case of the dolphins, you identify the popular ones and the cohesive dolphins, that keep somehow the network connected, right? Ivan is gone, I guess.
Oh yes, I thought you were talking to all of us, so I did not feel compelled to answer. But yes, of course.
So popularity versus cohesiveness. Okay. Okay. Good. Good. I think we can
I
continue.
want to, Luis Fernando, I want to make two important observations.
Good.
The first one, these two researchers for building this network, they spent 7 years, okay? They spent 7 years. They have to go to the sea, they have to, okay, a very exhaustive analysis of how the dolphins, for example, could you imagine how could manage to to find out which dolphin was friend of other dolphin? They have to spend hours and hours seeing the dolphins, okay? 7 years in the, and let me share my screen because if
Sure.
there was something that happens when they were doing this research, and I want to tell you that. You are seeing my screen?
Yes, we are seeing it now. Looking at
Okay,
it.
here is the dolphin network. This is between the centrality. And in the middle of the investigation, this dolphin disappears. They don't find it, and he remains 6 months, okay, disappeared. This dolphin returns after 6 months again to to their friends. When this dolphin was disappeared, this network was nearly destroyed. O sea, the all the dolphins, the behavior was very different, and this was not premeditated. This was something, I don't know how to say it, because something that happens. They not expected, unexpected, something unexpected. So in the article that they wrote, they wrote all these incidents, and it's a very famous article, because this is a very special social network. Okay. Okay. Let's continue. Okay, this is the last centrality that we're going to talk about. Eigenvector centrality. This name it's a little strange. This eigenvector had to deal with linear algebra, vectores propios, eigen is propio, eigenvector centrality. It's a little mathematical, but it's very intuitive also. Let's see. Degree centrality is myopic, ignores the place of the node in the network. Okay? Takes into account not only the number of connections a node has, the eigenvector centrality takes into account not only the number of connections the node has, but also the importance of the nodes to which it is connected. So the eigenvector centrality is, in a way, an improvement of degree centrality. As a result, nodes with high eigenvector centrality are often perceived as prestigious or influential within the network. In social networks, individuals with high eigenvector centrality are often influential, opinion leaders, or trend setters. Nodes with similar eigenvector centrality scores are likely to belong to the same community or module within the network. This can help uncover hidden structures and relations within complex networks. Okay, helps identify key players in the network who have indirect, this is important, indirect influence through their connection to other influential nodes. That these guys was what I was talking 10 minutes ago about the president, about the mayors, and about people that could be consultant to them. Okay, this is the type of centrality, eigenvector centrality. Okay, a question. This is a very simple network. Node 2, Node 4, and Node 6, all these three nodes had degree 3, okay? Which of these nodes has more power? And why? I want to in the chat, or if you want to raise the hand, or if you want to talk. Okay, let's think a bit. It's seeing this network.
Well, may I speak?
Yes, yes.
I think it is interesting to notice 4 and 6 are, what is the term you people use for this? I do not remember, but there is a technical word for it. Anyways, they are the same thing. I mean, they are placed exactly the same way.
Symmetrical?
Yes, it's something like that. I saw something. I saw, yeah, I saw something. The prefix is ISO, I think. So, anyways,
Isomorphic?
uh, not quite, right? Because that doesn't make so much sense, I think. But the point is that they are indeed symmetrically placed within the graph. Uh, so I would find myself inclined to think node number two is more powerful
Okay.
somehow.
Okay.
Let me-
Number two is more powerful. Any
Right.
other opinion?
Yeah, Manuel says number 4 and Laura. Manuel and then Laura. Manuel, explain
Yeah,
why.
Laura said number four.
I
Okay.
think that number four, because as you just said, it is not like the direct influence by the indirect influence. Because, for example, four could be seen as the like the assessor of number two, and number two can get to number one. But if we take a look at number six needs like an extra node to get to number one. So the one that has the most influence, let's say, it could be number four because it has the most connections and it can get to most places in shortest in less nodes than others.
Okay, and Laura,
Okay, that's a very good
explanation.
argument. Very good argument. Any other?
Laura, you say number 6. Can you give an explanation on it?
About the
The power.
statement, the other difference, I changed my answer. I
Okay,
think
so
is the best for.
you say number 4.
You change
Yes,
to four?
yes.
Change to four?
Yes.
Yes, because
You were
the
convinced by your
my response, yeah, my answer. Yes.
Classmate.
okay.
I think the best notes is number 6 because I think it have more indirect influence over notes, and the paths for the influence is less than the other option.
Okay, it's a very good argument that had to do with paths. Okay, let me say that there are a lot of arguments for 2, 4, or 6. If you are talking with three sociologists, experts in social networks, they could not reach a final answer. Okay, there are a lot of reasons, and if they know the network and they know the persons in the network, that could be. So this is not an absolute. What I'm going to do now is not an absolute answer, but is the answer given the answer that gives rise to this eigenvector centrality. Let me show you. Look. Here, number 4 is the winner. Okay. But what are these numbers? These 2, these 3, what are these numbers? If I sum 3 plus 3 plus 2, I get 8, okay? I am summing the degrees of the neighbors. Node 6 has degree 3. Node 2 has degree 3. And node 5 has degree 2. So the sum of the degrees of the neighbors are 8. In 6 is 7, and in 2 is 6. Okay? I guess this 7, wait a minute. I guess this 7 is here down. I don't know if it is clear. If I sum the power of the neighbors of 4, the power is 8. If I see power as the degree. But here is 7 and here is 6. It is clear? So the new power of 4 is the sum of the power of the neighbors. So decentrality is based that the importance of the node depends of the importance of the neighbors. It's a recursive definition because the power of the neighbors depend on what? On the power of the neighbors, okay? And etc. Okay. Let me
Professor,
go to this Excel model.
Professor, before continuing, maybe like in the other measures, if anybody can give an intuition or an explanation why this can be useful, can we? Yeah, why the power? What does it mean? The power? What? Why is it useful? What situations would that be useful? The power, the centrality measure. Guys, anybody can give any explanation or what information it could give you regarding the network that can be used for in some particular application or something like that?
I think using the example that the professor made, mm, if you are closer to a person with power and you are closer to a more than one person with power, your power is greater or higher.
Higher, okay.
Okay.
Okay, thank you,
Okay.
Daniel. Freddy also has an explanation. Freddy,
Maybe it shows how well connected are the neighborhood of mine.
okay.
Yes.
Yes, that's a good way, another way to put it. Yeah, nice. Thank you.
Neighbors are important. Any more
Explanation.
commentaries?
Manuel Peña has a.
Okay.
I don't know if this is a good example, but for example, the a web search like Google or Bing, because you, instead of going to the site directly, that is the site that you need, you go to the site that has the more power because it has all the connections to all the other sites. So you go to Google or you go to Bing, and from there you go to the site that you need.
Okay, that's a very good example. A
Daniel,
very good example.
Daniel.
The experiment is the same. I mean, yeah, you're looking for the one that has the friends with more friends with in many contexts. So, for example, the search engines, but also in political scenario where you want to be influential among the all the group of people. So you want to be connected to people who have more people connected to them. So I think that's the main idea.
Good, thank you. Another good example.
Okay, perfect.
I think we can go to Excel now.
Okay, look. This is how we can calculate the eigenvector centrality. Look, initially there are 6 persons or 6 nodes. Initially, I'm going to assign a power of 1 to all of them. Equal power. Equal power. What is the next level? The power of each of 1 6 node, that is one, is going to change depending on the neighbors. So here, for example, node number 1 has only node 2. So node number 1 has the power, has one power, the power of 2. So here's a 1. Node 2 is the sum of 1, 3, and 4. 1, 3, and 4. The sum of the power of 1, 3, and 4 is the power of 2. It's clear? Here, node 3, 2 and 6. Node 4, 2, 5, and 6. Okay? Node 5, 4, 4 and 6. And node 6, 3, 4, and 5. So the initial power was the same, and the structure of the network implies that these are the new powers. Okay? And what are we going to do now? With these numbers, we're going to calculate again using the same formulas, the new power, the new power, the new power. Okay? If I replicate this calculation, I replicate it 10 times. Here I can see Okay, here is the power in 10 iterations. Okay, you can see here that node 4 is winning. Okay, if I divided these numbers by the maximum, that is 13605 is the maximum power, that is number 4, I obtain a number between 0 and 1, and this is the eigenvector centrality. It's not exact, because if you want an exact value, you have to iterate 100, 1000 iterations. In the limit, when this tends to infinity, this gives the ideal values. And these values correspond to taking the adjacency matrix of this network and calculate the eigenvectors. It's an eigenvector of this matrix. But this is mathematical. I'm not going to show you. I think this is a very algorithmic idea, a very easy idea of how you can obtain the power of the nodes based on the neighbors. Okay, it's a very simple idea, and it's a very powerful idea.
Professor, we have a couple of mathematicians here. I don't know if you can complement the explanation regarding linear algebra and the meaning of, in this situation, I guess, Paula, are you there? Paula, and also Santiago. If they, I know Paula has stuff of this, like maybe give an intuition or an explanation about the eigenvectors here in the case of graphs, the meaning of that. What do you actually get from that, Paula? Paula? Or you can write the explanation there on the chat. And Santiago, have you studied this linear algebra and that? Santiago? Santiago? I mean, when you compute, as Professor said, you compute the power of the adjacency matrix, and then you compute the eigenvector. I guess not. Hernan. Santiago? I guess not. Well, if you can, please give some intuition there on the chat, and we can move on, Professor. Professor, are you speaking or are you muted?
Okay, no more questions?
No, I guess.
I have a question, sorry.
Okay.
Why, I mean, under what circumstances ought we to iterate more in computing the metric? Like, I mean, why wouldn't it suffice for a tiny graph such as the one of the spreadsheet to just iterate, I don't know, a couple of times perhaps?
Okay, this algorithm, this iterative method of calculating the power of the nodes converge very rapid. Is in 8-10 iterations, you get 2 or 3 decimals of precision of the real eigenvector centrality. So it's very efficient. The convergence is very rapid. Obviously, the software that calculates the eigenvector centrality uses the eigenvector because it's more. There are packages of linear algebra, and it's calculated not in the. I showed you the iteration method of calculating the eigenvector centrality because I guess it's very simple, and it's very illustrative of why is this centrality. I mean, why this How is it generated, this centrality? You understand eigenvector centrality when you see this iteration, because you are seeing that the power of a node is calculated based on the power of the neighbors, and this is going change and change, okay? But this is not the official way to calculate it. The network X and Gephi calculated in a mathematical way, I mean.
Yes.
But I I want to show you this because it's very simple and it's very pretty, I guess. That was the
Professor
reason.
Freddy
Okay.
has a comment or a question. Freddy?
I got a question. The algorithm always is give a solution, or maybe there are some cases where there is no solution for the eigenvector.
That's a good question. I think that uh, every network that you have, you can calculate the eigenvector centrality. There's no restrictions, because you calculate a matrix that is guaranteed to have that eigenvector. So always exists this eigenvector centrality. No problem. I
And
don't know.
Ivan also has a question or comment. Ivan?
Yes, thank you. So a different question is, would you say this metric is like a composite metric on the ones we discussed prior to this one? I do not know if my question is clear.
Could you repeat it, please?
So you're
Yeah,
asking whether this is another centrality measure. That's what you're asking?
I mean, kind of, but not so much. I am having here, Paula bro, something interesting on the significance of this measure, but I wonder if it is like how could I put it? If it somehow builds up on some of the measures we discussed before of closeness, betweenness,
Okay.
etc.
Okay. No. Look this paradox. This measure was invented by sociologists and people working in social networks, and it's a mathematical measure because because okay, this eigenvector centrality is his origin has nothing to do with the other three. This centrality was born in sociology in a group of researchers that were trying to find new measures of centrality and has not to do with the others. Let me tell you that I know about 12 different centrality measures. These are the four most important, but there are others depending on the diffusion centrality, CATS centrality, uh, and there are a lot of centralities. And but the four that are most used are these four. Okay. Okay, let me show you a little bit another application of these centrality measures, and we're going to pause then the 10-minute break. Okay. I'm going to see the application of these centrality measures to diffusion and to vulnerability of networks. Okay. Are you seeing my screen?
Yes, we are.
Okay.
Yes.
Okay, I'm going to put here a network. Okay, this network. Uh, I'm going to attack this network. I'm going to attack it with the nodes that have minimum degree. Okay. 20% of these nodes are going to disappear. The nodes that have minimum degrees. Look, these are these nodes. They are going to disappear. Okay? And look that the network remains stable. Okay? It was not destroyed. Okay? I rebuilt the original network, but now I'm gonna attack this network with the nodes of maximum degree centrality. That. And you can imagine what is going to happen. Okay? Look. Okay? It's a little dramatic example that the centralities and these measures are important. Okay? In vulnerability, if you remove what is called the hubs, the network is completely destroyed. Okay? Here you can play with the other measures, eigenvector centrality, betweenness, and you can see it's interesting to see what differences are between them. If I put eigen or between, for example, could destroy more or break the network in more parts, and you can play with this. You can play in this model with this. The other aspect is diffusion, okay? For example, betweenness. I'm gonna choose some nodes. These are persons, and I'm gonna make sick some persons like this. So these are now with COVID, for example. These are the 7 nodes that have the most betweenness centrality in this network. Okay? And I'm gonna see what happened with the infection. Okay? Lot, 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 lot. Okay, in 5 ticks, in 5 iterations, all nodes infected. And this is the evolution. It's important, the evolution. And these are each day, the maximum infected each day. Okay? Let me, the same network, but I'm gonna choose, for example, maximum degree. Same initial diffusion. Look. Okay. Similar diffusion. So betweenness centrality and degree centrality in this case are not very different. But maybe because this network is very small. I don't know. Let me show another. These are the nodes that have less degree. And let me see what happened. Okay, there's a difference, no? Look, the peaks here were earlier than here, and the evolution was. This is studied very much. Remember that last week when there was your presentations, they were talking about viral marketing and diffusion, and this is a very interesting problem, a very complicated problem. When you have a network, what nodes are the best for diffusion, or what are the best for attacking, etc. And you can see the different centralities and compare them. And there are a lot of studies, depending on the context, that said for these type of networks, the best is node with between centrality cause the most harm to a network or the less harm to a network, etc., etc. So I want to show you this as another application of the centrality measures, a very important application in diffusion of information or of a disease in a network and in vulnerability of the networks. Okay. I don't know if there are questions. If not, we are going to do a break.
To have a break, yes. Any comments, any questions before we go to the break? I think very nice, Professor.
Is there any possibility that we have access to the examples that Professor Alfonso showed us?
To these models?
Yes, Professor.
Okay, I'm going to show you how. Look.
Thank you.
In the web page, when you see, for example, slides, what is network science? Okay, the first slide we presented. It's a zip file, because in these zip files, what is in these zip files? The presentation in PowerPoint and all the net logo models that I'm showing you. The only thing that you need to see and to play with the models I am showing you, it's the following. Net logo. It's a software. Excuse me. Net logo. If you put net logo, you go directly to the website. Okay. It's a little slow. Okay, homepage. If you download NetLogo here, it's free, no virus. It's so if you have this version of NetLogo and you download this zip file, you could open the presentation, and when there is a link like this link, like this link that I have here. Oh, wait a minute. Okay. And when you see this link, you click and you can see the model. Okay. If there's any problem, you could mail me and I. Okay.
Thank you, Professor.
Okay. Any other questions?
Maybe just because Oscar was asking. So all these resources, the presentations, the readings, the examples, the links to the repositories and such are on the website. So Classroom is mainly for hosting the assignments and for the fora, okay? The discussion fora.
Okay.
Okay, and I just posted the link there, though it is on the Classroom as well, just the link. So you can get to all these examples and all this information. Okay, so it's 7:42. So we'll meet back in 10 minutes. So 7:52.
Okay.
Kind of stretch a little bit. Thank you. Okay, especially we are back. We can continue then, Professor.
Okay. Okay, are you seeing my screen?
Yes, we see some there's some notebook, right?
Yes. Okay, I'm going to show you a little bit this important library of networks. It is called Network X. It's it's in Python. It's a very popular library for analyzing networks. This is a Jupyter notebook. Uh, and I'm going to show you a little bit the basic functionality of the library. Uh, Today is of much help the chat GPT. You can ask, for example, I for example, look at this. Look at this. This is is the dolphin? No, this is not the dolphin. Okay, this is a small network. I guess it's called the Karate Club Network. Wait a minute. This is very big. Oh, wait a minute. Okay, here you can read a network. You can visualize it. Very basic commands. Here you could visualize the different centralities of the network. Let me run again this one moment. Okay. Let me put one moment this here. This is a small network. It's called the Karate Club Network. It's in the library of NetworkX. It's a standard network. You could visualize it. And here, excuse me, here, you could see the different centralities of the network. The degree centrality, the between centrality. Okay. I recommend you this library because it's very powerful and it's very well documented and it's very easy to use. Most research articles that have to do with networks work with this library. Also, our libraries in R, in language R. iGraph is a library in language R. There are a lot of libraries, but the standard for analyzing networks is this NetworkX. Okay.
Yeah, and
Okay.
Professor, this is a very important tool, like for the mining projects exercise that they have to do. So it's it's
yes.
There are some algorithms already implemented there, like the centrality measures. The calculation of the centrality measures is something that you can do very easily. Can you please maybe stop a little bit on the calculation of the centrality measures there?
Okay.
Once you load the network, then what you can perform this type of analysis just by using just one single instruction there allows you to compute the centrality measure.
Okay, I have to confess that this piece of code was made by ChatGPT. Okay, with 3 or 4 questions, he gave me this code. So I don't know. Uh, but look, 2 weeks ago, I found this. This program is called YED.
Professor, just to make sure, Oscar, just to emphasize that, Oscar is asking whether network S is on Python, and yes, that's true.
Yes, it's in Python. It's in Python. Yes, is typically you load the network X and the matplotlib that is for drawing and and all these graphics are this is use matplotlib. So you need, I guess, these 2 libraries, and if it's and if you're working in something a little more specialized, there are other libraries. For communities, for example, are 10 algorithms, different algorithms for communities. Not all algorithms for communities are in the basic library, so you have to call another library. But what I want to show you, it's, I don't know, 2 weeks ago, I found this tool. It's very similar to Gephi. And I guess, I'm not sure, but I guess that is better than Gephi. Look, this beautiful, for example, this is Dolphins network. This is between a centrality, but if you want degree centrality, look. Layouts, look, this is very beautiful. Look this, for example, radial layout of the network. Look, this is the Dolphin network in a layout that is radial. Okay, but I wanted, I don't know, circular, normal. This software calculates. Okay, this software is not as complete as Gephi, but in terms of visualizing and doing things very fast and very beautiful, it's a very good tool. I have used it for 2 weeks. I discovered 2 weeks ago, and I'm not very expert in this, but this tool is integrated with Neo4j. It's part of Neo4j, and so this is supported by a very important company. Neo4j it's a company, but I'm going to put here one moment. Neo4j is the worldwide leader in graph databases. So okay. Uh, 1 or 2 weeks ago, we talked about this. I guess some of you told us that they have worked with this Neo4j, and this YED, YED is the software that visualizes and is integrated with databases. But I am using this only for visualizing, and it has an editor. I can edit the network. For example, I can do something like this, And okay, I'm going to calculate the centrality measure, page rank centrality. It's a very important, but we have not seen it, and this is the and you can calculate communities in networks. So I don't know, but I guess that with time I'm gonna replace Gephi with this. But I'm not sure because Gephi is very powerful and has a lot of years being the leader of the okay Gephi. No, this is Gephi. So here we have and if you do something like this, I guess this is very beautiful also. Okay. So Gephi, and I'm gonna put in the chat the name of the new. I'm gonna put in the chat the name of the two tools for visualizing and analyzing networks. Okay, Gephi and YED. Okay, okay. We are going to talk in this hour that is left in this session about global measures of networks. Global measures. Uh, let me. Okay, global measures of a network. Why global measures? Here are some questions. How robust is a network to attacks or failures? How long information travels in a network? How centralized is a network? How many clusters does a network have in terms of communities? All these questions have to do with global measures of networks. Look this question, what it means that a network is well connected. Let's begin with this question. Look here. This on the left is a fully connected network. It has 3 nodes. And this at the right is sparsely connected. It has 650 nodes. But look, what is the average degree of this network? Well, degree 2, degree 2, degree 2. 2 plus 2 plus 2 divided by 3, average degree 2. This network also has average degree 2. What I'm trying to say is that these are two very different networks and have the same average degree. Okay? So perhaps this is not a very good measure of a network. Or at least for these two examples, this measure, that is a global measure. What is the average degree of a network? Each node, you sum the degrees of all the nodes and divide by number of nodes. It's very simple. Okay? Let's move to density. To quantify the difference between the two cases, these two cases, network scientists define the concept of network density. What is the density of a network? Well, for example, here the density is 100% because all the edges that are possible to connect between nodes are connected. How many connections could I do here? 3, no more. Here, how many connections could I do? This with this is missing, this with this. If all nodes of this network were connected to all other nodes, the density was 100. But if you want that all nodes of this network are connected to all other nodes, you need this number. 210,1925 connections. Okay? But this network has less connections. If you divide the number of real connections over the number of possible connections, you get the density of the network. I don't know if this is clear. For example, here, number of connections, free. Number of possible connections, maximum number of connections, free. Free divided by free, 100%. Okay. So average degree, the same. But with density, we began to see differences. In density, these two networks differ, okay? The density of a network seems to go down as you increase the number of nodes. If you have networks with few nodes, typically the density is high. But if you have networks with a lot of nodes, the density is less. Real networks, this is an important point. Real networks are sparse. What is sparse? Low density. This is an example. The routers forming the backbone of the internet. How many routers form the backbone of the internet today? 192,244 nodes. What is the possible number of edges with that nodes? The formula is number of vertices times number of vertices minus 1 divided by 2. This is the maximum number of edges that I can connect to a network with B nodes. Look this number, this huge number. In reality, how many edges connect these 192,000 routers? This number is the real number of edges. If you divide this number by this, you get this density of the backbone of the internet. Okay? So typically, big networks have low densities. Okay? Real networks are sparse. Sparse, low density. Okay? Look this example here. This is the World Wide Web. This is from nearly 10 years ago. Number of nodes in the internet. This is number of edges. Look, maximum number of edges is 10 to the 12 with this number of nodes. And the real is this. If you divide this number by this, you get 10 to the minus 6. Okay? 10 to the minus 6 is 0.000001. That's the density of this network. Okay? This okay, this is the average degree, but it is not important in this.
So can we ask them? I think there are plenty of examples to give us like a couple of 2 or 3 networks, examples of networks where you can actually see that they are very sparse. Real world examples, networks. Anybody? Does anybody have an example? Maybe a couple of examples? There are plenty of examples where you can actually tell that they are sparse. Anybody?
The power grid.
Okay, go ahead, develop.
Power grid.
Explain it, please.
Yeah, because I think that there are some main hubs, but But yeah, there are a lot of places on the rural zones that they are not so connected
Yeah, that's a
to
good
the
example.
ones.
Yes.
Yeah, like the distributed the electricity, right? One.
Yeah, that's correct.
Yeah, exactly. So that's where you have the centrals and the poles, with the cables and all that. Yeah, so it's very sparse. Another example, somebody who let me see who raised your hand. Who was it? Anybody else? There are plenty of examples.
For example, roads between cities, because you have to go through different cities, yeah, in the country to get from one to another. They're not a road that connects every single city to every other city.
Exactly. That's another example. Santiago. Thank you. Another one, final example. Yeah, Santiago was saying in the chat also professor referred to it, the scientific citation papers. Yeah, I think those are good examples. Most of them are actually like that. Thank you.
Okay. Look this table. Look this column. These are densities 1, 2, 3, 4, 5, 6, 7, 8, 9 of 11 real world networks. Look, for example, this second network is the IMDb movies and stars. Is the database of movies and stars. I guess it's very well known. It's a place in the internet. Look the density. Here is US air transportation. Is the network that joins the airports. Telegans, remember the brain of this little worm, 0.03. So this is important. Real world networks are sparse, have very low density. Okay. Density is an important measure. It's an important global measure, but there are more important. This this is one of the most important today global measures of a network. Look, density doesn't solve all ambiguities in the case of the average degree. Look this example. Two networks can have the same density and the same number of nodes, but end up looking quite different from each other. Look, this network at the left and this network at the right both have 13 nodes and 32 edges, but they look very different. Here, for example, two communities, they look very different. That is why network scientists created a new measure that is called the clustering coefficient. Okay. The clustering coefficient of this network is 0.8 and of this is 0.4. So the clustering coefficient, in a way, reveals the difference between these two networks. Okay, let me talk about clustering coefficient because we have not defined the clustering coefficient. Let me go to another presentation to show you the clustering coefficient. I guess it's this presentation. Let me see. Okay. 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 Here it is. Clustering coefficient could be considered as a centrality measure, I guess. It's a kind of, look, I'm gonna, where is node 3? Here is node 3, okay? Look, node 3 has degree 3, has 3 neighbors. The clustering coefficient of this node measures how well connected are the neighbors of this node. Look that this red node has these 3 orange nodes. How many connections are between these 3 nodes? 2. Okay? 1 and 2. How many maximum connection of these 3 nodes? How many are the maximum connection? 3, okay? This, and this, okay? 3 possible connections between the 3 neighbors. Of these 3, this network has only 2. So what is the clustering coefficient? 2 divided by 3. Let's see if it's okay. 0.67. Let's do another example. Another node. Okay. I'm gonna, excuse me. I'm gonna load the network again. I'm gonna choose node 5. No, it's very complicated. Excuse me. Node 2. Okay. What is the clustering coefficient of node 2? By the chat, you could tell me, or if you want me to explain it again, I could explain it again.
Please, can you explain it again?
Yes. Look, I'm gonna do this. Forget all these blue nodes. Let's concentrate in this. This node has 3 neighbors. These 3 neighbors, the maximum number of connections that can have these 3 neighbors are 3 connections. This with this, this with this, this with this. If these 3 connections were real, the clustering coefficient of this node is maximum. The clustering coefficient of a node is maximum when all the neighbors of the node are all connected between them, okay? All friends of this guy is each of these 3 friends are mutual friends, so okay? But of the 3 possible connections, maximum possible connection between these 3 nodes that is free, only 2. So the clustering coefficient is 2 divided by 3. Let me show an example of a node with 4 nodes. For example, node 4. Look, what is the clustering coefficient of this node? How many friends, how many neighbors? 4. When I have 4 nodes, what is the maximum possible number of connections when I have 4 nodes? Let me do it here. When I have 4 nodes, what is the maximum number of connections? 1, 2, 3, 4, 5, and 6. Okay? It's clear? 6 connections. How many connections are between these 4 nodes? 1, 2, and 3. 3 out of 6 possible. Of 6 possible connections, there are only 3. 5 and 7 are not friends. 7 not friends. 3 yes and 3 no. So the clustering coefficient of this node is 50% or 1/2. Let's see. Okay? 0.5. Clear or not clear?
Yes.
Node 1. No, excuse me. Erase. Gonna load it again. Node 7. Look. What is the clustering coefficient of node 7?
1.
1. This node has 2 friends. How many connections between 2 friends? One connection, one friend to the other, and exists in the network. So this has maximum clustering. Let's one more and no more. This with 5, with degree 5. This is node 5. Okay. This node has 5 friends. What is the maximum number of connections between 5 people? This, okay? How many connections are there? Yes. Look, if you have 5 nodes, each node has degree 4, and 4 plus 5 is 20, okay? Am I right? Four plus 5 is 20, but if you divide by 2 because each edge, this edge counts for 5 and counts for 2. So each edge counts twice. Okay, forget all that. The total number of edges is 10, okay? If you want, the formula is, again, n times n minus 1 over 2. Okay, 10 connections. How many connections are there? 1, 2, 3, 4, 5. Okay? Am I counting right? 1. How many orange edges are? 5? Am I correct? Guys? 5? Yes?
Yes or no?
Yes.
Yes.
Yeah.
So of 10 possible connections between 5 nodes, this 5. So again, the clustering coefficient of this node is 0.5. Okay?
Okay.
Okay. We're going to talk a lot about the clustering coefficient in this course. This is a first contact to the clustering coefficient. What is this 0.872? Okay, for example, clustering coefficient of this node. Please. In this network. Huh?
Hello.
1.
It's easy.
1.
One, because all the neighbors are interconnected, and of this one, this is not one. Because this is a neighbor, and they are not connected. This is less than 1. This is less than 1, but all are 1. So if you sum all the clustering coefficient of all the nodes and divide by the number of nodes, you get 0.872. And this, if you do the same, you get a different clustering coefficient. So in a way, the clustering coefficient is revealing differences in the structure of these two networks. It's saying, in a way, this network is more clustered than this. Okay? I'm not expecting that you understand fully this concept. When I, some years ago, were introduced to this clustering coefficient, what is this? I don't understand. But, okay. So we have seen some global measures. This
One,
average degree, not very important. Density, more important. Important to know that networks are sparse. Examples. And clustering coefficient,
one has a,
one of the most important measures of a network.
one has a
Yes?
question, Professor. One, Ramos.
Yeah, I remember that some minutes ago you asked how to, yeah, something related to how to know if a network is well connected. Can we say that if the clustering coefficient is higher from the network A compared to the network B, the network A is better connected?
Yes, yes, you anticipate what I was going to say. Thank you.
Okay.
Yes, yes, yes. Exactly that. Look this question. In general, networks are sparse. Density, very, very small. Average degrees, also very, very small. Wouldn't you expect that real-world networks have a low clustering too? The surprise is no, the opposite holds. Real-world networks are clustered. Okay? Let's concentrate in this column, okay? This column is the clustering coefficient of these networks. Look, 0.59, 0. Look, 0.1, listen to me, 0.1 is a high clustering coefficient. A low clustering coefficient would be 0.000. These are coefficients high. This is not so high, but it's not bad. We're going to see later, it's not bad. Okay? So this is an important point. Density, low. Average degree, well, here is not the average degree. Low, bad clustering coefficient in real-world networks. In real-world networks. So the clustering coefficient is a very important measure. Okay? The nodes could have few connections per node, but these connections tend to be clustered in the same neighborhood. That's the important thing. Communities. Nodes tend to close triangles. Clustering coefficient is typical of social systems. High clustering coefficients. Okay? Let's turn to another important global measure. we have talked a little bit about in previous sessions is the degree distribution of a network. Here is a scatter plot. Here is the degree distribution of this simple network. Okay. X-axis, the degree. Y-axis, number of nodes that have this degree. So this network has one node of degree 1, of degree 3, one node, and of degree 2, 3 nodes. Okay? Very easy to calculate. The number of nodes with a particular degree. Okay. Sometimes this is drawn not as a scatter plot, but as an histogram. So you have one bar here, one bar here, one bar here. Okay. These are examples. For example, this here, this is a regular network. What is a regular network? A regular network is a network where all the nodes have the same degree. Here, all nodes have degree 2, so obviously, and this is the histogram. Look. All nodes have degree 2. This is a similar example as before. Okay, let's change to a more complicated network. This is the protein network, a famous network that is studied very much. And this is the degree distribution. Here I don't have the data, excuse me, I don't have the data. I forgot to put in the slide how many nodes and how many edges has the network. And I don't remember. Let's see if I could find this data because it's important. I'm gonna try to open the, where is the network? Okay, I guess it's here. No. Okay. But it's very big, I don't know how. Okay, it's here. Let me view properties, I guess. Okay, here we have the data. 2,061 nodes, 7,182 edges, okay? It's a very disconnected network. Okay, look the distribution. This distribution is revealing. It's this side of the distribution is saying there are a lot of nodes with few degree, with a small degree. And there are very few with very, very high degree. What is the name of these nodes, please? It has a name, 4 letters.
Hubs.
Hubs. These are the hubs, okay. Nodes with very, very high degree, 90. Degree 90. And there are a lot. But look, something interesting that I have commented, I guess, before. Here in the y-axis, in this case, is not the degree, but something I guess more important is the probability. It's like a normalized, this is a normalized degree distribution, where it's not important the number of nodes, but the percentage. Look, this point, what is saying? Half of the nodes of this network have degree 1, okay? 0.5. It is more important to say half of the nodes of this network have degree 1 than saying 800 have degree 1. It's clear, okay?
Yes.
And what we said before, no? Doing Drawing that like this, the degree distribution with probabilities and not with real degrees, make it easier to compare two networks with a different node count. Okay. So this is typical. Is I repeat, it's like a normalized graph, normalized degree distribution graph. Okay. These are degree distribution of some real world networks. Look, they are very similar. This first one is co-authorships in scientific publication. It was published by a neuroscientist called Yurel Leskovec. This B is co-appearance of characters in the same comic book. Okay. There are researchers that investigate comics as networks. These are interaction of trust between PGPs. I don't know what is PGP. Do you know what is PGP? It's a network. I don't know. This is the distribution. Slash dot. Anyone knows a slash dot? It's like a social network. I don't know. But this is the distribution. Look, they are similar. Okay, I don't know if there are questions about this before going to the next.
Professor, maybe I think it's important that they, or to highlight rather the importance of the distribution, because when you look at the distribution, it tells you in general information, useful information about the global the connections of the network of the nodes, right, along the network, around in the network. So the distribution, the degree distribution is important. So as a histogram, in general,
yes,
you some information about the distribution of the data or whatever you have, the values of the variable. So it's important that you keep that into account, because take that into or rather that you pay attention to this, because it's another way. Sometimes it's especially when you have huge big networks, then it's hard to see what's going on inside the network. Like we've seen some of them, those examples, right? With a lot of connections, and you don't see what's going on there inside. But here with the distribution, you get it, some general information about how their nodes are connected.
Yes. Let me show you more distributions. Oh no, excuse me. This is clustering coefficient. Is this model? Wait a minute. Okay, the cursor. Okay. Here in this model, this no. Okay. Oh, I loaded twice. Okay. Think it's the same. Okay. I'm going to load dolphins. Okay, dolphins. This is dolphin network. Look the distribution. It's not Gaussian. It's not normal. It's a very small network. Look, average path length 3.3. Okay, clustering coefficient of dolphins 0.25. Okay, 0.25, 0.26. Clustering coefficient of the dolphin network. For example, this type of network, it's a very important network. we are going to see later. Uh, the degree distribution is similar to the protein. Lots of nodes with small degree and the hubs here. Small world networks. These are very, I guess, the most important model. The most important model of networks is the small world networks. Let's see. Let's see. Look how is the network. It's more or less regular. All nodes are nearly the same degree. So the histogram. Okay, this is the degree distribution. This, for example, this is no. Okay, that gives an idea. Experts in network science said that if you are very expert in network science, when you see this distribution, you can visualize more or less the network. So you say, oh, okay, an expert in network science said, okay, the network is, this is a very important measure of the network. It's a global measure. Average path length. Average path length is also a very important global measure. I guess let's go here. No, I guess this is an old presentation. Let me go to the 1 second to the new presentation of global properties. I guess it's this. Sorry. No. Okay, let's see this model, and I'm going to show you other global measures. There are a lot of global measures. I'm going to show you some. Let's choose this network. Okay. For example, here is we have talked about it. No, I guess no. We have talked about the diameter of a network? No, okay? No.
No, we haven't.
Okay, here it says the diameter of this network is 6. Could someone of you tell me what could be the meaning of the diameter of a network? How to define it?
Manuel, can you explain your definition that you suggest? Manuel, can
Yeah, well, in the diameter is the measurement from edge to edge in a circle, for example. So I guess that the diameter here would be, if we extend the network, like the shortest, no, but the longest path. I wrote it the wrong term. The longest, the one that is has the more nodes across the path. I don't know.
Yes, exactly. Is the longest, shortest path. The longest, shortest path. This 6 means there are two nodes here. For example, this, I don't know, this. And this here. There are two nodes in this network that the shortest path is 6, is very long. I guess we could see this in a smaller network. I think this is too big. Okay. Diameter of this network, 9. I guess diameter and radius are understood by a concept that is called eccentricity. Look, this is another centrality measure, eccentricity. It's a measure of each node. What these numbers mean? This is 5, this is 7. The eccentricity of a node is the length of the longest shortest path that begins in the node. I guess that for this node is 1, 2, 3, 4, 5. Okay, this is the longest shortest path. This node because this is 1, this is 2. Okay. This is 5 also because the longest shortest path, I guess, is, oh, no, this is 4. 1, 2, well, I don't know. It's more or less, but look at that the longest shortest path that originates from this node is 9 because from here to here, I guess, there are 9. Okay? It is more or less clear what is the eccentricity of a node.
I have a question, Professor.
Okay.
Just to clarify, so among all of the shortest paths between all nodes, it's to find the longest. Among all the shortest is to find the longest. Is that the meaning of that?
Of the diameter.
Of the diameter. Ah, okay. And the eccentricity is for a particular.
Okay.
Is the same
The
for a particular.
eccentricity is a local measure because you talk about the eccentricity of a node, but you talk about the diameter of a network. Okay? But look here. What is the maximum eccentricity? 9. Yes? 9 here, 9 here. This maximum eccentricity is the same as the diameter. What is the minimum eccentricity? 5. This is the radius. So maximum eccentricity, diameter, minimum eccentricity, radius.
Okay, I understand. Thank you.
Look that this has to do a little with clonus centrality. I guess nodes with the minimum eccentricity, they have the maximum closeness centrality. I don't know if this is true, but it has a relation, you see? Look here, the density. This is a very sparse network, density 0.09. Okay. Let me show you two important concepts, the core and the periphery of a network. The core is like the core is the central part of the network, the heart of the network. And the periphery, look, if I do click here, this is the core. The core corresponds to all nodes that have minimum eccentricity are part of the core. So this is the core of the network. And periphery is all nodes that have maximum eccentricity are the periphery. Core and periphery. Let me show you core and periphery of a bigger network. Let's see. For example, this. Okay. The core. Look, the core is only one. This is the one with minimum eccentricity. The periphery, the free with maximum eccentricity. This is the core, this is the periphery. Let me, this network, for example, it is very difficult to try to guess the core because, look, okay, here the core are 1, 2, 3, 4, 5, like 10 nodes in the core. And in the periphery, I guess 6. Okay. Let me one more concept and we finished.
Professor,
one very important concept. I'm very.
Professor Alfonso,
Yes.
eh, eh, the expression longest shortest is still confused to me. Why longest shortest? It's not only the longest.
Professor, and by the way, I was gonna ask that as well. I mean, like rather to emphasize that because Freddie Feria there, he said the shortest, longest path. So is it the same, the longest, shortest path, or than the shortest, longest path? And why that
Okay,
would
I
that would
guess
be acceptable or not?
it's very difficult to
Maybe with an example, I don't know, maybe a small example. Can you maybe, or one of those examples, like the one you just showed, right? Maybe you can tell.
Okay, let me try to draw something here.
Yeah. Yeah. Why not the longest? Yeah. Why not just the shortest rather?
Oh.
The longest you say.
Oh, wait a minute.
Because the longest could be very. I mean, there are ways to because you can go around. So the concept of the path is very well defined, you know, in graph theories, in graphs.
Let me draw. Okay, something like that. I don't know. Erase this. What is the diameter of this network?
Four.
4.
4 or 3? Okay, shortest paths. This is the shortest path from 2 to 3, length 1. This is another shortest path, length 1. This from 3 to 5, this path, 3, 4, 5, is other shortest path. Is the shortest path from 3 to 5, okay? So we have here a shortest path of length 1, a shortest path of length 1, a shortest path of length 2. If you put in a set all the lengths of the shortest paths and choose the largest number, that is the diameter. You have to consider all the shortest path between the nodes. I guess here are shortest paths of length 4? No, I guess all shortest path. Okay, that's interesting. Is there a shortest path of length 4 in this network?
No, there
For
there
example,
is a path of 4, but the shortest is 2,
Three.
3.
exactly. Look that from 1 to 5. Oh, the shortest path is here. From 3. Oh, there are no shortest path of length 3.
Maybe from 2 to 5.
I guess it's okay, thank you. From 2 to 5. Thank you. From 2 to 5, this path 2, 3, 3, 4, 4, 5 is the longest shortest path of this network. I don't
There are
know.
actually two, right, Professor? There are actually two paths from 2 to 5 of length 3.
There are various shortest of
Yeah,
length
because
3.
if you go
Yes.
through node 1, right? Same.
Okay. 2, 3, 1. Okay. There are two shortest paths of length 3. 2, 3, 4, 5. 2, 3, 1, 5. What is the longest shortest path? Okay, there could be more than one longest shortest path. Here are two paths. Here are two shortest paths of length 4, but no of length 3, excuse me. But there is no shortest path of length 4.
Professor, because
So
they
the diameter is 3. I don't know if it's clear.
Professor, they say why not the longest, right? Because, for example, if you
Okay.
go from 2 to 5 to 1, what is the longest path from 2 to 1?
Okay.
The longest.
4.
Okay.
You said 4. You said
It's a
4.
very interesting question because the notion of longest path does not exist in network science. I don't know why. I don't know why shortest paths. Well, shortest paths are important because are efficient. If you want to go from Bogota to Cali and you go to Ecuador and Peru and then go to Cali, okay, you could visit wonderful cities. But if you want to go to Bogota to Cali, the normal thing is doing in the longest, excuse me, in the shortest path that is passing La Línea, okay? So shortest paths are important because of efficiency. Longest paths, it is interesting to research this week from here to the next session if there is bibliography about longest paths. I don't, but it's a very interesting question because maybe longest paths in a network could have importance, okay? But I don't know. I don't know if it's clear that. It's a very good question. Why shortest and no longest? Okay.
Professor, I guess we need to finish, but
Yes.
I think we should set up tomorrow a discussion forum about these centrality measures and global measures. You know, some questions and also generate discussion around about these concepts. I think that would be nice.
Luis Fernando, one last thing, please. I put in the chat a PowerPoint presentation of an analysis of centrality in a network of researchers. It's a very small network. Let me show you, because I forgot. Give me 2 minutes, please.
Yes, an example.
Uh, One second. Okay. Are you seeing my
Yes.
my screen?
Yes.
Okay.
Centrality measure is an example.
I put in the chat this presentation, McCulloch Social Network Analysis. Okay. Look, it's this network. It's a real network. Evan, Brian, Colin are researchers of a university, I guess. It's a real network. And this presentation talks about analysis of centrality of this network. It's a very, very good example, similar to the Dolphins network, okay? But this is a little bit more extensive, more extensive, okay? So I invite you to see this PowerPoint presentation, and when you read it, you are going to understand more the difference between these centralities. And in the next session, in next Wednesday, we could begin commenting that, or we can put it in the forum, Luis Fernando.
Yes, I think we
We
wrap
can
up
open a forum
questioning
about questions about centrality, and also about this analysis that is very interesting. Okay.
Right. Yes. Yes.
Okay.
I'll select this question forum for based on this presentation regarding these concepts that we said today. Okay. Good. Very nice. And I think next time we'll continue with some other concepts. Professor, can we please stay a couple of minutes? Okay. So I'll thank you everyone, but I will ask this student Daniel Mello, who is just to stay just for a couple of minutes.
Yes, sir.
Well, stop, and everybody else, thank you so much and have a good